Well, so welcome to the last week of this particular lecture series, and in this particular week we will specifically be dealing with the different analytical models which are available, or rather which are widely used in two-phase flow and in macro systems, but how they can be applied to microsystems. But before that, there is a small portion which I could not complete last week, but I am very tempted to share it with you. So, we will be discussing that particular portion regarding the effect of wall wettability on two-phase hydrodynamics, and then we will be shifting to the other hydrodynamic parameters. Now, as I had discussed in the last class, if you remember, I had discussed a lot about the wall wettability characteristics, and I found that when the pipe was hydrophobic, naturally the liquid did not want to wet the pipe wall, and so large number of other flow patterns they emerged, and the rivulet flow pattern came up. Now, just to demonstrate that in a better way, we performed our favorite Taylor bubble experiments in a hydrophobic tube, where the contact angle was about 110 to 115 degrees, and we found that a very interesting metamorphosis of the Taylor bubble took place in this particular case. If you observe the Taylor bubbles, we find that the Taylor bubbles, they are axis symmetric bullet shaped in the circular pipe, and the same pipe with the same dimension when it was a glass pipe in which we had performed the experiments, and the same pipe when it was coated with silane to give a contact angle of around 115 degrees, we found that the shape of the Taylor bubble underwent quite an interesting change. Firstly, if you remember, in the previous case, we had a hemispherical nose. We have shown it a number of times. It was something of this sort. It had a hemispherical nose and a flat tail. In this particular case, we find that the cap, it undergoes a transformation and develops into a corner sort of a thing, unlike the nice rotationally symmetric shape in a hydrophobic pipe. And at the same time, we find that the tip, it shifts from the liquid center or the liquid axis to one end, and immediately it begins to expand to occupy the maximum area between the bubble and the wall. Okay. So, therefore, what happens? The first thing is there is a change in the nose of the shape, and which automatically tells us that definitely then the rise velocity should also be changing in this particular case. We do not have a nice rotationally symmetric bubble in this case. We find that it has developed into a corner, and it has shifted from the tube axis to one particular wall, where it immediately touches the wall and then immediately tries to spread out. And at the same time, what happens? The continuous annular liquid film which was there, we find that the liquid film, now it is no longer continuous. It gets disrupted, and the liquid is compelled to flow down as a rivulet along the bubble surface. The rivulet which I was talking about, it also assumes this particular shape. If you observe the rivulet, it emerges from the tip of the corner, it changes its course randomly, and it produces a curious meandering pattern which is somewhat similar to the free end of a garden hose. Isn't it? If you observe it, what do you find? You do not find the annular film. You find that the liquid film, as the bubble it comes in contact with the tube wall, the liquid film, it falls down as a meandering pattern, somewhat like when you water the garden, the way it comes out from a garden hose, it usually takes up that particular shape and generates a moving three-phase contact line which makes an angle with respect to the overall direction of propagation of the bubble. While the bubble is flowing up, we find that the three-phase contact line, it is not in the direction of the motion, but it makes an angle with respect to the overall direction of motion and it continuously changes its orientation as the bubble moves vertically up. And we find that this particular meandering tendency, it is maximum for the vertical case. As we tilt the tube, we notice that the liquid it just has predominantly one particular space to flow down. So, therefore, as the tilt increases, we find that the meandering tendency that also decreases with time. Interestingly, if we try to find out the rise velocity of the bubble, what we find? We find that in a hydrophobic tube, the initially when the tube diameter is very small, as we all know, I have already discussed that for any particular tube there is a critical diameter below which the bubble does not rise. Now, this diameter is a function of Yordwas number. This diameter is different for a kerosene bubble, it is different for a air bubble, it is different for some other liquid bubble. It is dependent upon the properties of the confining fluid and the rising fluid. So, naturally, we know that there is some particular critical tube diameter below which the bubble remains stationary, it does not rise, right. And this particular critical diameter, it is different for a air bubble and it is different for a kerosene bubble. And this is a function of Yordwas number. Several researchers have suggested different critical Yordwas number at which a bubble rises. Now, we have observed that the critical diameter is higher for a hydrophobic pipe, right, because it is quite natural, because when will the when will the bubble rise? It will rise by the downward displacement of liquid. And so, naturally, the liquid, if it wets the wall, the displacement becomes easier. So, therefore, when it does not wet the wall, naturally it is very difficult for the bubble to pierce the liquid and rise and force the liquid to fall as a film. So, as is evident from this particular graph, if you observe, we find that for a hydrophilic pipe, the critical diameter is lower as compared, for a hydrophobic pipe, we find that the critical diameter, it is higher as compared to a hydrophilic pipe. Or in other words, the bubble rises due to buoyancy at a higher diameter, or begins to rise with buoyancy at a higher diameter in a hydrophobic as compared to a hydrophilic pipe. But once it begins to rise, the rise velocity in a hydrophobic pipe is higher as compared to the rise velocity in a hydrophilic pipe. So, therefore, there are two things which need to be kept in mind in this particular case. One is decretic higher for hydrophobic pipe. So, therefore, a bubble will rise, hydrophobic tube, or in other words, a bubble will rise or begin to rise at a higher diameter when the tube is hydrophobic, but for d greater than d crit, UTB in a hydrophobic tube is greater than UTB in a hydrophilic tube. Along with that, what we wanted to do was, we also wanted to see how the bubble responds to abrupt changes in pipe wettability. For this, what we did, we took a pipe and we half the portion of the pipe was silenized, as a result of which the first half of the tube was hydrophilic, the second half was hydrophobic, or vice versa. So, we performed experiments with a hydrophobic section preceding a hydrophilic section and a hydrophilic section preceding a hydrophobic section. And very interestingly, what did we observe? We found that when it was rising through the hydrophilic section, the bubble assumed the nice rotationally symmetric shape. Then moment it entered the hydrophobic section, the first change occurred in the nose, because the nose first came in contact with the hydrophobic wall. Immediately moment it entered, the nose, initially it was trying to maintain its spherical shape. Initially it did not want to rupture the spherical shape, but the liquid, it was unable to maintain the continuous film. So, the liquid meandering it started, and gradually the nose, with this liquid meandering, as it gradually traveled towards the top, the nose was pushed to one side and it formed the typical open corner shape that we had observed previously. On the other hand, when it first was rising through a hydrophobic section, the typical shape of a hydrophobic section was there, and moment it entered the hydrophilic section, immediately the nose, it took up the semicircular hemispherical shape, while the film continued to meander in the lower portion, and then gradually as the bubble progressed completely into the hydrophilic section after a while, we find that it resumed its the rotationally symmetric shape which it has, or rather with which we are familiar with. So, therefore, this was one particular thing which I thought I should be sharing with you. And the other thing also which I would like to discuss in very brief is, as we all know that in microchannel slug flow is predominant. So, I thought we should also be knowing that when slug flow occurs in a particular microchannel, how the slug parameters get influenced with wall wettability, conduit diameter, and your different ratios of the water and the kerosene phase, this particular as well as with water and the air phase. So, therefore, in this particular case we find that more or less experiments have been done with oil water and air water, and the slug parameters, they were measured, and it was observed that the slug parameters, the distribution of the slug parameters, they were then plotted, and the different slug characteristics, they were then observed in this particular case. So, very briefly I will try to just show the situation. Suppose we take the situation for equal flow ratio of the two. What do we find for equal flow ratio? We find that more or less the majority of the slugs, they have the same size, and there are very few slugs which are larger than the average size, right. But when we increase the diameter, we find that this particular peaked character, it disappears, and the slug size varies over a larger size range, which suggests that with increasing diameter, tuning of the different slug parameters becomes difficult in this particular case. Again, we find that for QW by QK, where W is water and K is kerosene, we find that when we come to lower QW by QK, we find there is a more remarkable influence of water velocity. In this graphs, what we have done, we have plotted them for different flow ratios, and for each flow ratios, the legends show different water velocities. We have plotted them for QW by QK equals to 1 and less than 1 and greater than 1 in a polymethyl methacrylate serpentine channel, and we have also, rather not we, I am very sorry, these particular researchers, they have also performed experiments in a stainless steel channel. They have performed experiments in a PMMA serpentine channel for 2 different diameters, and apart from doing experiments on water kerosene, they have also done experiments on air water flow. from these experiments what we find is that when QW by QK, the flow ratio of water and kerosene is not equal to 1, the influence of flow rate is much more drastic, as you can observe from these two graphs. We find that for each of these we find that the flow rate, the influence of flow rate is much more drastic, as the curves, if you follow the curves for different flow rates, whereas in for QW by QK equals to 1, it's more or less the flow rate, the influence of flow rate is not so drastic, and when we increase the pipe diameter we find that the slug sizes can vary over a wide range. So, therefore, monodispersity is not maintained in this particular case. Very interestingly, if instead of a PMMA serpentine channel we come to a stainless steel channel, we find that the distribution becomes more or less Gaussian in nature. And in this particular flow the influence of your flow parameters, rather the flow rate, it is not as pronounced as in this particular case. And again we find that if we come to air water flow for and this one more thing, if we are working with stainless steel conduits, we find that the general slug size is smaller as compared to the PMMA conduit. This is something very interesting. I should note that these stainless steel channels, they are comparatively more hydrophilic as compared to PMMA channels, and we find that the slug sizes in this case is smaller because the wetting characteristics, they strongly influence the slug size, and therefore, this shows that the effective interfacial area available for mass transfer increases for the stainless steel as compared to the PMMA channel. This is one particular interesting thing, that just by manipulating the wettability, we can actually change the interfacial area available for different mass transport processes. The other thing is, as we increase diameter, we find that the size varies over a wide range, and also along with that we have observed that lower internal circulation occurs for a higher pipe diameter, which explains why the mass transfer decreases as we increase the pipe diameter. And so, in conclusion, if we need to discuss the results, the conclusions will be, firstly, that the channel aspect ratio, it has a strong effect on slug size and other hydrodynamic properties. We find that the slug size distribution, it's more or less Gaussian at all flow rates and at all QW by QK ratio in a hydrophilic stainless steel pipe, while in a PMMA channel it strongly relied on the ratio of QW by QK, and we also found that there was no specific trend in the large aspect ratio PMMA channel. Further, we found that the dispersed phase hold up, if the hold up is computed from these particular distributions, we found out that the dispersed phase hold up, it went through a maximum in the stainless steel channel, but it decreased continuously with increasing QW for a PMMA channel. And the slip ratio for liquid-liquid flow, that is greater than 1 for stainless steel channel, and the reverse happened for PMMA channels. Now, this portion of the information I wanted to share with you, because this would give us sufficient insight into how to engineer the wall surface and obtain the not only the flow pattern of our interest, but also to modify the slug parameters in order to increase the interfacial area even when the same flow pattern is existing, right? Because we found that interfacial area, it increased at when we use stainless steel channel, and then so therefore, by playing with all these things, we can attempt to rather to increase the transport properties just by changing the conduit material in an intelligent manner. Well, so this completes our discussion on the effect of operating parameters on the flow morphology. It was quite long, at almost a week long discussion. I hope you haven't been much bored with it. So now we come about to discuss the effect of operating parameters on void fraction and pressure drop. Now, in this regard, I would like to remind you that void fraction depends upon the flow morphology or the flow patterns. So, therefore, we find that the influence of input parameters on void fraction is more intimately related to the change of flow patterns than to anything else. For example, void fraction, it has one particular sort of a relationship with, say, increase in gas and liquid velocity, but we find that the relationship changes with flow pattern more than the superficial velocity. As expected, void fraction will increase with gas superficial velocity, it will decrease with liquid superficial velocity if we are dealing with air water systems. But the nature of the curves are expected to be different for different flow patterns, and the influence of operating parameters on void fraction, it primarily depends upon how they influence the flow morphology between the phases. Now, let us see, more or less quite a good number of work has been performed, and the general characteristics which have been observed, number of researchers have done, there are some contradictory results, but the general trends I would like to discuss. This trend, it gives you an idea regarding the how void fraction it behaves with the inlet volumetric fraction, or in other words, as I have already mentioned in the nomenclature, how alpha varies with beta and how this variation again depends upon the channel dimension in the micro domain. Now, if you observe in this particular part, we find that for the larger channel, we find that more or less the data, all the experimental data, they are lying on the 45 degrees line, which shows that for comparatively larger channels, alpha equals to beta over almost the, I should write, over almost the entire range of beta ranging from 0 to 1. This is quite evident. Now, when we see that alpha equals to beta, what does it automatically imply? It implies that the in situ and the inlet compositions are the same. Now, if you again go back to my initial lecture, what did I say? That when the lighter fluid tends to slip past the heavier fluid. If you remember, I had mentioned this, it is in the slide of my introductory lecture, and when this lighter fluid tends to slip past the heavier fluid, naturally what happens? The inlet velocity of any particular fluid, which is defined as the superficial velocity, will not be equal to the in situ velocity for either phase 2 or phase 1, right. And we had defined beta as u1s by u1s plus u2s. Now, from this particular graph, if we find that alpha is almost equal to beta, then what does it imply? It implies that more or less alpha can also be predicted from the inlet conditions, and this hints at a no slip condition, or rather a most better way to describe is no interfacial slip condition. So, therefore, if such a condition exists, it means that the two fluids are flowing as a single unit, or the two fluids are flowing as a pseudo fluid with suitable averaged properties. So, therefore, if we have to develop a model for this particular fluid, what we can do? We can assume the two fluids to be flowing at the same particular velocity, and we can just say that the density of the fluid rho Tp, this can be determined from the inlet void fraction in this particular form. And therefore, if you remember the single phase momentum equation that I have written down, that same particular single phase momentum equation should be applicable in this particular case, where rho is replaced by rho Tp, u is replaced by UTP, and therefore, this particular model, it is known as the homogeneous flow model, where we assume the two fluids to be completely mixed and flowing at the same mixture velocity, and in this case the single phase momentum equation is applicable with suitable average properties. So, we find that for the two larger pipe dimensions, more or less this particular homogeneous flow model is suitable, but the deviation from the homogeneous flow model gradually increases as the pipe dimension decreases. Here alpha is almost equal to beta for most of the cases. Here also it is equal to beta, but the deviations particularly at low beta begins to increase. But if we further reduce the channel dimension, we find that the variation changes completely. In this particular case, we find that alpha is in no way equal to beta, and the curve suggests a very strong influence of slip, which needs further discussion. We will be continuing our discussion on the void fraction characteristics as well as on the pressure drop characteristics in our subsequent lectures. And we will be, in very brief, we will be discussing the homogeneous flow model. We will be incorporating the slip in the homogeneous flow model in order to make it little more robust, and we will discuss what are the different models, or rather how these particular models can be applied to microchannel flow in our subsequent lectures. Thank you very much.